Compiler construction number 15. So last time we introduced functions, new top-level functions, and we went through all of the R passes that we need to implement it. Today what we'll do is we'll talk about the C and X passes that we need and the modifications that we need to make to the C and X languages. So we're going to be going from C2 to C3, and basically what we're going to need to do is modify expressions, tails, and the program structure. So expressions are going to be modified in the following way. We're going to introduce the funref form, which is going to have a label, and we're going to have the call form, which has arguments. We're going to have the tail form. It is going to be modified to have a new thing, which is a tail call. Arg dot dot dot. Then what we're going to do is we're going to have definitions in the C language, just like we have in the R language. So we're going to have a define with a label, and the label has variables with certain types and a return type. Then we have some info about this particular function. Then we have a mapping from label to tail for that particular function. Finally, we have programs, where a program is some info, a sequence of definitions, and then a label that we're going to start the program with, which is going to be main. Okay. Now, when you extend your interpreter to work on these, there's nothing really that interesting that you need to do. The main thing that you need to do is you need to, of course, implement calls, where how it'll work is that you'll evaluate the first position, it'll evaluate to a function reference, and then you'll go look up in your global map of definitions into that function, and then you'll jump to its begin or main label or wherever. You'll have a designation of which label you should start with. If you want, what you could do is you could stick an initial label right there as the label that you start this particular function with. Okay. Now the next thing that we need to do is we need to actually do the econ pass. So the econ pass, it only has a few special things that we need to do. So when we call econ on an R program with some info and some list of definitions, and then of course an application of the funref main, then what we'll do is we'll turn that into the C program with the same info, where we're going to call econ D on each one of the definitions, and then stick in the name main. Okay. Now, how do you do an econ D? So econ D is going to, take the definition. This is a R definition, of course, of some function f with some arg0 with type 0 up to arg n type n with the return type and then the body e. Okay, and what are we going to return? Well, we're going to return a C definition, so it's going to be a define, and it's going to have the same name, f, the same arguments, arg0 type, arg n type. The result is still going to be the same, the return type. But now what we're going to do is we're going to return the L mapping. And the L mapping is going to be the result where we say that, the L mapping prime. So we'll get L and T from calling econ E of E, and L prime will just be equal to L, where we expand it with a mapping from body to the tail. Okay? So essentially, the exact same thing that we used to do for programs, we're now doing for individual functions. Because basically the way that our compiler is going to work now that we have functions is that each function is like a little instance of a program before. So all of the logic that we used to do for programs now happens on individual functions. Okay, the only thing left that we need to do is talk about how econ works with applications. And it's fairly straightforward. When we call econ E and we give it a let of x equals some application of the operator and the operands inside of some body, what we do, is we just turn that into a set thing of, a sequence of a set of x to a call of the rater and the rands, and then we do econ E of the body. So just like all the other cases. All right, and now what about when we call econ E and we end up with an application at the bottom? Well, this right here is a tail application. So in that case, we can generate a tail call. A tail call to the operator and the operands. In this tail call, okay. The next thing that we need to do is we need to expand 15.3. We need to update uncover locals. Uncover locals. So this is going to operate on functions rather than programs. So it is exactly the same, except you're going to do it once totally independently on every single function. Because like I said before, what we're doing is we're making it so that the things that we used to do for programs, we now do for functions. And that's going to include register allocation. We're going to do register allocation independently of every single, each function is going to have its own register allocation. So now we're ready to talk about how to change the X language. So we're going to go from x2 to x3. We're going to update the argument type, so it's going to have a function reference as a new case. And that is a function reference with a label. We're going to add 2 new instructions. And these new instructions are going to be an indirect call queue of the argument and something that's going to be called a tail jump to a label. Okay. How do we compile each one of these, or how do we emit them? When you emit an indirect call queue of some argument, that turns into call queue star of the argument. So for instance, it might look like call queue star of %RBX. If this argument ends up being installed in a register, then it would be that. But now you're going to have a little special case, which is that you're going to say that when there's an indirect call queue to something that is known to be a function reference, then in that case, you'll just generate a normal call queue. And then how do you compile a function reference? Well, you compile a function reference. So if we omit a function reference label, then we just omit that as the address. So I guess it would be the label %RIP. It might be the case that we might need LEAQ here. I'm not sure. I forget. Yeah, I don't know. You'll find it out. So put a note right here. When you omit this, you're gonna start off omitting it like that, but you might find it to be the case that like the only time that this thing is ever going to show up is it's going to be a move queue. So you might need to detect the situation where you're move queuing a function reference into something and actually turn that into a load effective address. I forget. Okay, but now let's talk about tail jump. So how do you omit a tail jump? What is a tail jump? The idea of a tail jump is that if you have a function f and it ends by calling a function g, like our even odd function is like this, then that means that after we're done calling g, we don't need anything left over from f. So because of that, we can actually totally get rid of all the memory associated with f. So what we can do then is we can free the stack space. And so the way that we do that is, let's think about the way that programs / functions start. They start off by saying, first there's begin, and what it does is we save the callee save registers, okay? Then what we do is we allocate the stack space by doing, well, hold on, we save those. Then what we do is we move queue our SP into our BP. Then we allocate the space, so we do a sub queue of the space that we need, SS, from RSP. Then we jump to the body. Okay, then inside of the body somewhere, we have a jump to the end. And then what the end does, what it does is it's going to add queue of the stack space, %RSP, and then it's going to restore the callee registers, and then it's going to do a return queue. Okay. What we're going to do when we see a tail jump is we are going to, like a normal call would be inside of body somewhere, and it would just say call queue, to, G or something like that. And now call queue G is going to go jump inside of the G code, and then that's going to do a bunch of work, and then we're going to come back from a return and then jump, and then that's going to do this add and do this restore. But what we're going to want to do when we see a tail jump is we're going to want to directly do a jump to the label. Now if we directly do a jump to the label, then that means that we're going to pop in to this code right here, which is going to start off by saving its callee registers, allocating its own stack space, going through, and restoring its own stack space. Which means if we do that jump, then this stack space is never going to get restored, so we're going to leak memory. So what we want to do is we want to make it so that we actually restore that memory right now. So that means that we have to take this code right here, which we call the postlude, And we need to take that postlude and we need to stick it right here. Now, you might say, if we just stick this code right here, is that going to like mess up any function calls that we're going to make? It's not going to make up any function. It's not going to mess up any function calls that we make because these instructions are going to modify all of the callee saved registers, which is going to make it so the arguments to this function can't possibly be stored inside those. Because what will happen is that what we're going to do before we do this is we're going to move all the arguments into the appropriate registers, and then at that point um, they're now in the argument registers, and those argument registers are caller saved registers, meaning that this code isn't going to affect them. Okay, so what this means is that inside of your emitter, you're going to have to keep track of what the postlude ends up being. Now this is going to be kind of annoying because it essentially means that your emitter has to be like sensitive to what function it's inside of so it can output the appropriate SS right there, right? Because that SS is going to be, dependent on whatever, whatever the actual stack space this thing ends up needing, which of course you don't know, at every point in the program, because you only know that after you've done register allocation. So, okay. So what do we want to do next? Okay, so let's talk about doing selection of the instructions. So 15, 15. Okay, so here's what we're going to do. So let's make it so that, we're going to make it so that select P of some C program, I, definitions, and then some label, right, is just going to equal the X program where we have I, we're going to map select D over the D's and then just leave the label there. And then select D is going to take our definition, which has some info, some function, some argument 0 with some type 0, ... argument n, type n, and then it has the return type, and then it has the mapping from label to tail, and then it has, the label that we start with, so the begin label. Or maybe you just know it's always begin. Okay, and what we're going to do there is we're going to return a new definition, and this is going to be an X definition, with I, and then the function, the arguments go away, and then it's going to have a label to block mapping. We'll call it label to block prime, and we'll have to know what the initial start label is. All right, where the label to block mapping is the result of calling select T on this label to tail thing. So basically we're going to go through each one of these and we're going to convert those tails into blocks just like we used to do. Then what we're going to do is we're going to create a new, this is label to block prime. We're going to take the label to block mapping and we're going to add a new label, and we'll call this one start or begin or something like that. And what it's going to do is it's going to be a block that's going to do the following. It's going to have some info, and it's going to do a move queue of R0 to A0 up to move queue R5 to A5, where R is the vector of that says the order of the argument. So it would be RDI, RSI, RDX, RCX, R8, and R9. Then what it's going to do, let's actually move this out of the way. Let's move that. Let's just put it up here as a little note. So this right here is the arg ABI registers. So it tells us what order the registers come in. So we move each one of those registers into the appropriate arg, which of course is a variable, which means that later on, when we do register allocation, these guys are going to appear in the move graph. So that's going to bias these arguments to actually appear inside of those registers. Okay, then what do we do after that? What we do after that is we're going to jump. We're going to jump to the begin label. In order to make it so that its end, so that the new end, so inside of this begin label, there's going to be, we're going to have returns, right? And so those returns, they are hard-coded to move something into RAX and then jump to end. Well, in this case, rather than jumping to end, they're still going to jump to end, but our new end is going to end with a return queue. Actually, I guess it already did end with a return queue. So I guess we don't really need to comment on that. So we'll erase that. So the idea here is that individual functions will turn into this little tiny preamble that sets things up so that the registers appear, so that the registers that are the actual ABI registers get moved into the argument variables, so then the rest of the program will see them as they're supposed to be. Okay. So next what we need to do is we need to talk about actually selecting for a call and selecting for a tail call. I guess those are the things that we need to do. So that would be 15.6. Okay, so when we call select E of a destination, and the code is a call to a rater and its RANs, then what we're going to do is we are going to start off by doing a move queue of argument 0 to register 0 up to a move queue of argument 5 to register 5. Now it's not literally register 0, it's the one that's the ABI one. Then what we're going to do is we're going to do a call queue, and this is an indirect call queue, on the select A of the operator. Then what we're going to do is we're going to do a move queue of RAX into the destination. Now in contrast, what if we had a select T and we ended up with a tail call of the operator and the operands? Well, this right here, let's just call this let's just call it 1. So we're going to do everything that was in 1, but then after that, we're going to do a tail jump to the select A of the operator. Okay, so if we see a call, we load the arguments, and then we do an indirect call queue and then move RAX to the destination. Or what we do is if it's a tail call, we do that same argument loading, and then we do the tail jump. And of course, that tail jump we know is going to get turned into that postlude that restores the stack, and then a concrete jump. Okay, what do we need to do next? 15, 17. So the next thing that we need to do is we need to update our register allocator. Basically, the only thing that we need to think about differently is how to build the interferences. So the way that we update our thing that finds conflicts is we need to say what does it do to tail jumps and what does it do to call queues. So a tail jump, it writes callee saves registers. That's what it does. And what call queue does, call queue is just the same as before. So actually the only thing that we really need to do, an indirect call queue, it reads the argument. And then it does everything else that a normal call queue does. So essentially, these two are just like call queues, except that we know that nothing is live after a tail jump because it's the end of the program. So it's kind of a simple case. We know that V is going to be empty in those situations. The only thing that really matters is that it's going to read the arguments, and then an indirect call queue, it reads the argument that is the operator. That's the argument for the rater. Okay. What else do we need to do? Oh yeah. Okay. So we need to do the assign home stuff. And essentially, assign homes, it needs to do some of the job that main used to. Because remember that what main used to do is it used to like allocate the stack space and stuff like that. That is going to now be taken care of assign homes, because what will happen, it'll happen per function now, whereas it used to only happen per program. So basically those jobs get rolled into this. What else do we need to do? Patch. I don't think there's anything really interesting that patch needs to do differently, because tail jump, just takes a label, and an indirect call queue, only looks at one thing. What else do we need to do? Oh yeah, one of the things you're going to need to do is update your runtime, because your runtime, it's going to have a new thing for a type of a function, and you'll have to have some way of printing out functions. Now, my advice is to just print out a function as something like, it's a function. Don't actually say what it is. And I actually use the syntax hash sign bracket function. And then sometimes what I'll do is I might print out what the type is, just so that's kind of like a helpful debugger. But yeah. So this is going to be one of those things where when you get down to really doing this, there's actually not a lot to describe, but there's so many interlocking pieces that it's going to be really easy to think that you've got everything right, and then find some horrible problem when you actually finally do all of the integration, and that was my personal experience. I realized when I was doing these final steps that I had made mistakes earlier, so it took like an hour to do these things that should have been really small if I noticed the mistakes earlier. All right, so we now have top-level functions. And in this sense, our language is basically like C right now. And why do I say, well, it's like C except that it has a garbage collector. And what I mean by that is that we have a fixed number of top-level functions, and those fixed numbers of top-level functions, they, you can get pointers to them. That's what function references are. So what we'll do next time is we'll actually extend this further to have closures, and that's what we'll do next.